Welcome to week 9 of Fundamentals of Python and Machine Learning. In this lesson, we are covering Chapter 10, Unsupervised Learning Clustering using K-means. In previous chapters, our models learned from examples that included known target values or class labels. This week, the data will not provide the answers. Instead, K-means will examine numerical similarities and attempt to organize observations into groups called clusters. We will study how the algorithm works, how to select a possible number of clusters, and how to interpret the results carefully in a real-world context. By the end of this chapter, you should be able to distinguish supervised learning from unsupervised learning. You should understand what clustering is and how K-means groups observations according to numerical similarity. You will learn the iterative K-means process, initializing centroids, measuring distance, assigning points, recalculating centers, and repeating until convergence. You should also be able to prepare and scale numerical data, train K-means using Scikit-learn, access the assigned cluster labels and centroid coordinates, and assign new observations to clusters. Finally, you will learn how the silhouette coefficient can help compare possible values of K and how clustering results should be interpreted in relation to real business needs. Supervised learning uses labeled examples. A regression dataset includes the numerical value we want to predict. A classification dataset includes the correct category for each training observation. Unsupervised learning does not provide those target answers. The algorithm receives feature values and attempts to discover structure within them. Clustering is one form of unsupervised learning. Its purpose is to identify observations that are more similar to one another than to observations in other groups. Because no correct cluster labels are supplied, interpretation becomes a major part of the workflow. Unlabeled data contains feature measurements but no target column that tells the algorithm the correct answer. For a clothing sizing problem, the dataset may contain waist circumference and upper leg length. It does not tell us whether each person belongs to size small, medium, large, or extra large. The algorithm must examine the measurements and identify possible groups. The discovered clusters are not automatically meaningful categories. People must examine the results and determine whether the groups are useful, responsible, and appropriate for the problem. Clustering organizes observations into groups based on similarity. A good clustering result typically places similar observations in the same cluster and separates observations that are less similar. The algorithm does not initially know what the groups represent. After clustering, we may examine the feature values, cluster centers, and distribution of observations to assign an interpretation. For example, one cluster may contain customers with similar purchasing behavior, while another contains people with similar body measurements. The meaning comes from analysis, not from the cluster number itself. K-means is a widely used clustering algorithm for numerical data. The letter K represents the number of clusters we ask the algorithm to create. Each cluster is represented by a centroid. The centroid is the mean position of the observations assigned to that cluster. The algorithm repeatedly assigns observations to their nearest centroid and recalculates the centroid. The goal is to create compact clusters whose observations are close to their assigned centers. K-means requires us to select the number of clusters before fitting the model. If k equals 2, the algorithm creates 2 centroids and 2 clusters. If k equals 4, it creates 4. Different values of k can produce very different interpretations of the same dataset. We can use evaluation tools such as the silhouette coefficient to compare possible values. However, mathematical separation is not the only consideration. The final choice may also depend on domain knowledge, operational constraints, fairness, cost, and the purpose of the analysis. A centroid is the mean position of all observations assigned to a cluster. For each feature, calculate the average value across the cluster members. If the points are 2, 3, 4, 5, and 6, 4, the average first coordinate is 4 and the average second coordinate is 4. The centroid is therefore 4, 4. A centroid is not necessarily one of the original observations. It is a representative average location in feature space. K-means follows an iterative process. First, initialize K-centroid locations. Second, measure the distance from each observation to each centroid. Third, assign every observation to its nearest centroid. Fourth, recalculate each centroid using the mean position of the observations assigned to it. Fifth, repeat the assignment and update steps. The process continues until the centroid movement becomes sufficiently small or another stopping condition is reached. The first step is to choose starting centroid locations. A basic implementation may select them randomly. Scikit-learn uses K-means by default. K-means chooses starting centers more carefully and is designed to improve initialization and convergence. The random state parameter makes the result reproducible. The ninit parameter controls how initialization runs are handled. Initialization matters because K-means can converge to different solutions depending on where the centers begin. For every observation, K-means measures the distance to each centroid. Euclidean distance is commonly used. For each feature, subtract the centroid coordinate from the observation coordinate, square those differences, add them together, and take the square root. The shortest distance identifies the closest centroid because distance controls assignment. The feature scales can strongly affect the result. We will address scaling before fitting the practical model. After calculating the distances, each observation is assigned to its nearest centroid. Every centroid represents one cluster. The assigned cluster can be stored as a numerical label, such as 0, 1, or 2. At this stage, the groups may not be stable. The initial centroids may not accurately represent the natural centers of the assigned points. The next step recalculates their positions. For each cluster, KMeans calculates the mean of the assigned observations. That mean becomes the new centroid. If the observations assigned to one cluster are concentrated in a different region than the original center, the centroid moves toward them. This update reduces the distances between cluster members and their assigned centroid. After all centroids move, the assignment step is performed again. K-means alternates between assignment and centroid updates. Some points may move from one cluster to another after the centers change. The centroids are recalculated again. The movement usually becomes smaller with each iteration. In practice, the algorithm stops when the centroids no longer move enough to exceed the configured tolerance or when the maximum number of iterations is reached. Convergence means the iterative process has stabilized. It does not guarantee that the discovery groups are the only possible or best real-world interpretation. K-means attempts to minimize the within-cluster sum of squared distances. Scikit-learn reports this value through the model's inertia property. A lower inertia means observations are closer to their assigned centroids for that selected K. However, inertia decreases as more clusters are added. If every observation had its own cluster, the distances could approach 0. Therefore, inertia alone does not determine the best number of meaningful clusters. K-means works best when the groups are reasonably compact and can be represented by their means. It may struggle with curved clusters, clusters with very different densities or sizes, and datasets containing strong outliers. An extreme observation can pull a centroid away from the main group. K-means also requires numerical features and depends on Euclidean geometry. Categorical values cannot simply be treated as meaningful distances without appropriate representation and a suitable algorithm. A clustering result should be evaluated, visualized when possible, and interpreted with domain knowledge. We can use make blobs to generate numerical data for a clustering demonstration. We request 3 underlying centers and 300 observations. The function can return known labels because the synthetic data generator knows how the points were created. However, we intentionally ignore those labels during K-means training. The clustering model receives only X. This demonstrates the unsupervised workflow. Feature measurements are available, but the target labels are not supplied to the estimator. Before fitting the model, we visualize the observations without cluster colors. This represents what the algorithm receives. We may suspect that groups exist, but the dataset does not provide labels to confirm them. In higher dimensional datasets, visual separation may not be obvious because we cannot display all features simultaneously. Clustering methods help examine structure that may not be visible in 1 or 2 dimensions. K-means is a distance-based algorithm, so feature scaling can change the clusters. Suppose annual spending ranges from 1,000 to 100,000, while store visits range from 1 to 20. The spending feature has much larger numerical differences. Without scaling, it may dominate the distance calculation even if visits are equally relevant. Standardization places features on comparable scales. The decision to scale should still consider the meaning of the features and whether equalized numerical influence is appropriate for the problem. Before clustering, select the numerical feature that should define similarity. Handle missing values using a justified strategy. The chapter's short example removes rows with missing measurements using dropNA. Next, fit standard scalar and transform the clean features. The scalar records the means and the standard deviations required to transform future observations consistently. Clustering occurs in the scaled feature space. When we later interpret the centroids, we can convert them back into the original measurement unit. Scikit-learn provides the K-means class. We specify the number of clusters, use K-means++ initialization, and provide a random state for reproducibility. The fit_predict method trains the model and returns one assigned cluster label for each observation. We can also call fit and then read the labels property. Because there is no Y target, the model is trained using only the feature matrix. K-means returns numerical cluster labels. Those numbers are arbitrary identifiers. Cluster 0 is not automatically the smallest, first, healthiest, or most important group. Another valid run or model configuration may assign different numbers to geometrically similar groups. If we want meaningful names such as small, medium, or large, we must examine the centroid values and establish a documented mapping. The interpretation should be based on the feature measurements rather than the raw cluster number. The cluster center property contains the centroid coordinates. Because our model was fitted on standardized data, those coordinates are expressed in scaled units. To interpret them as waist and upper leg measurements, use the scalar's inverse transform method. This converts the centers back into the original feature units. The resulting values describe representative average locations for the discovered clusters. They are not necessarily exact measurements from an individual person. After fitting, KMeans can assign a new observation to one of the existing clusters. The new data must use the same feature order and pre-processing as the training data. First, transform the measurements with the fitted scalar, then call the model's predict method. The return value is the numerical identifier of the nearest cluster. This is an assignment to an existing grouping, not a supervised prediction of a known correct label. For two feature data, we can visualize the assigned clusters. Each point is colored according to its KMeans label. The large markers represent the centroids. Visualization helps us inspect whether the groups are compact, overlapping, imbalanced, or affected by outliers. However, a visually attractive result is not enough. The groups must also be evaluated quantitatively and interpreted according to the problem. Selecting K is one of the central challenges of K-means. Too few clusters may combine observations that should remain separate. Too many clusters may divide one meaningful group into several small fragments. We can evaluate several values of K and compare the compactness and separation of the resulting groups. The silhouette coefficient provides one useful measurement. The selected value should also be assessed for stability, interpretability, and practical usefulness. The silhouette coefficient compares two types of distance for each observation. The value A is the average distance from the observation to the other points in its own cluster. A smaller A means the observation is close to its cluster members. The value B is the lowest average distance from the observation to the points in another cluster. That other group is the closest neighboring cluster. A larger B means the observation is well separated from its nearest competing cluster. The general silhouette coefficient formula is B minus A divided by the larger of A and B. This produces a value between -1 and +1. The book presents 1 minus A divided by B. That simplified expression is equivalent when A is less than or equal to B, which is the common well-clustered case. Using the general formula is more accurate because it also handles observations whose own cluster distance is greater than the neighboring cluster distance. A silhouette value near +1 indicates that an observation is close to its own cluster and far from neighboring clusters. A value near 0 suggests that the observation lies near a boundary or overlapping region. A negative value suggests that the observation may be closer, on average, to another cluster than to the one it was assigned. The average silhouette score summarizes the values across the dataset. Higher is generally better, but the average should not hide small clusters or groups with poor individual silhouette values. Scikit-learn provides the silhouette score function. First fit K-means and obtain the assigned labels, then pass the same feature metrics and labels to the function. The result is the average silhouette coefficient across the observations. The score can be calculated when at least 2 clusters exist and fewer clusters than observations are represented. We repeat this process for several candidate values of K to compare possible cluster counts. Test a reasonable range beginning with K equal to 2. For each value, fit a new K-means model and calculate the average silhouette score. The K with the highest average score is a strong candidate under this measurement. However, the word optimal should be used carefully. Silhouette evaluates geometric cohesion and separation. It does not know whether the resulting number of groups meets business requirements or whether the clusters are stable, equitable, or operationally useful. The chapter applies K-means to a clothing design problem. A designer needs to select a limited set of standard Bermuda short sizes. The available observations contain waist circumference and upper leg length. No predefined size category is included. Clustering can identify groups of similar measurements and calculate representative centroid values. Those centroids may help the designer propose as standard dimensions. The clusters support the decision, but they do not replace product design, customer research, manufacturing constraints, or fit testing. The shorts dataset contains missing measurements. Pandas can identify them with this null plus zoom. The chapter removes incomplete rows with dropna. Before doing this in a real project, examine how many records will be removed and whether the missingness follows a pattern. Deleting many observations may distort the population represented by the data. After cleaning, scale the two measurement features before applying K-means. In the chapter's example, the highest silhouette score suggests two clusters. Mathematically, two groups may provide the strongest separation under that measurement. However, a company may decide that two sizes do not serve a sufficiently broad range of customers. The designer may choose K equal to 4 to create 4 product sizes. This is not simply overriding the mathematics without reason. It is a decision to balance geometric cluster quality with customer coverage, manufacturing complexity, inventory cost, and product strategy. The trade-offs should be documented and evaluated. After fitting K-means with 4 clusters, access the cluster centers. Because the model used standardized measurements, inverse transform the centers into centimeters or the original units of the dataset. The centers can then be sorted according to a meaningful feature, such as waist circumference. Only after this inspection should provisional names such as size 1 through size 4 or small through extra large be assigned. The centroids are representative averages. A production design may need tolerances, overlap, additional body measurements, accessibility considerations, and fit testing before those values become manufacturing specifications. Let's summarize Chapter 10. Unsupervised learning works with data that does not include predefined target labels. KMeans groups numerical observations according to their distance from cluster centroids. The algorithm initializes the centers, assigns observations to the nearest center, recalculates the centroids, and repeats until the solution converges. Because K-means depends on distance, feature selection, and scaling can strongly affect the result. Scikit-learn provides K-means, fit, predict labels, cluster centers, and an inertia for working with the model. Cluster numbers are arbitrary identifiers and must not be treated as meaningful names without interpretation. The silhouette coefficient compares within cluster cohesion, with separation from the nearest neighboring cluster. A higher average score can identify a strong candidate for K, but it does not understand the business problem. In the Bermuda short case study, 2 clusters may produce the highest mathematical separation, while 4 clusters may better support the company's product strategy. That decision should be evaluated using customer needs, fit testing, manufacturing constraints, and responsible design. For week 9, complete the assigned reading, watch the lecture and demonstration materials, complete the guided practice lab activity, finish the independent practice assessment, and continue course 6 of the Google IT Automation with Python Professional Certificate. Next week, we will bring the machine learning workflow together by preparing a model for practical use, creating a client application, and completing the final project or exam.